I'm very happy to be here today with Dr. Venkat Viswanathan from Carnegie Mellon's Mechanical Engineering Department. Venkat and I have worked together over the last year to develop the first MOOC at CMU, and it was a project I particularly loved, so I'm happy to have him here today. I'm also happy to have with me Teresa Burridge and Aaron Frazier from the Learning House, who are working quietly in the background to make sure everything runs smoothly and that everybody can connect. So please let them know in the chat window if you're having any trouble, and they'll try to get you sorted out. And also, please feel free to write down any questions you have in the chat window as we go along, and we'll stop periodically to kind of review and see what questions are coming up. So the more interaction we've got here today, the better. Okay, so if that sounds good, let's get started. So we're here to talk about engineering education online, and as important and sought after as engineering degrees are all over the country and the world, engineering has been slower than most disciplines to move online. But that trend is changing really rapidly. And as more and more engineering programs move online, this is a really good time to ask, what are the necessary ingredients for developing robust, effective engineering courses in the online environment? So that's the question we're going to be addressing today, and it's also the question that Carnegie Mellon University was asking in 2012 when they spun out Akatar, which is a startup with a proprietary tech platform and also a suite of services for helping faculty develop online and blended courses. The leaders at Carnegie Mellon at that time weren't very happy with the available platforms for online learning, and they thought that maybe they could do better by leveraging CMU's technology prowess and also its foundations in the learning sciences. So Akatar was a result of that initiative, and Akatar really cut its teeth working with CMU's engineering faculty from the Electrical and Computer Engineering Department. And their input, the faculty input, was really influential in the design of our platform, as well as our process for working with faculty. Some of you know that Akatar was acquired by the Learning House in April, and the combined strength of both these companies together has really expanded our capabilities in all directions, and so we're very excited about that merger. So one of our most fun projects over the last year was to work with Venkat in developing CMU's first MOOC, Statistical Thermodynamics, which was offered through Coursera. And this picture shows the team of people who were involved. So on the left, we have 4 members of the Akatar team. We've got Venkat, our fearless leader, right there in the middle. Next to him are his 2 advisors and also his 2 TAs. So it takes a village to create a MOOC. And Venkat's going to tell you a little bit about this course and also where he's gone since offering it. Venkat?
Thanks, Marie, and thanks to Akatar and Learning House for putting this together and giving me the opportunity to participate in this and share our experience in trying to build online courses. So I want to start a little bit maybe around 2012. I was a graduate student at Stanford University, and this was around the time when there was the MOOC revolution. And at that time, I immediately was impressed by the MOOC revolution, and I wanted to try and build one. And 2014, I joined Carnegie Mellon University, and through the support of my department, I was provided with financial resources to build this MOOC. And Akatar joined this effort very early on, beginning of, or late last year, beginning of this year, and we began working on the project. The MOOC ran, as Marie said, on the Coursera platform. In April. It ran from April to June, and it was an absolutely great experience to run this class. We did one intentional thing. We timed our course such that it would follow another MOOC that was offered by Chris Kramer, who's an associate dean at the University of Minnesota, who offered a more introductory version of the statistical thermodynamics class. And the good thing that happened from this was that we inherited some of his learners, and that proved to be quite useful. Now, let's discuss some statistics about the class, and then actually the strategy helped quite a bit. We had over 6,400 people that enrolled from 136 countries. It was actually very fulfilling to see that over 36% of them were from emerging countries. What came as a very pleasant surprise to all of us was the completion rate. What is shown in the bottom panel is a plot of the views from the first module to the 11th module, which was the last module of the class. And there are two main takeaways from this. One is that we had nearly 20% completion rate. That is for the blue line. The other line is for people that enrolled in the signature track, which is a paid track. And so we had a completion rate of about 20%, which is far above the industry standard for MOOCs, which is around 5 or maybe 10% at best. And the second thing that you will notice from this is that once people cross the initial barrier of engaging with the first couple of modules, they often persisted with the class. And I think this was great validation that we did a good job of trying to engage the learners.
Great. Thank you, Venkat. And I also wanted to point out that since offering this course as a MOOC, Venkat is now offering it as a flipped course on the Carnegie Mellon campus, so he can speak to that experience as well. But the assets that he created for the MOOC have been useful in his teaching, his ordinary teaching as well. Okay, so what is necessary to develop effective online engineering courses? We're going to look at 5 ingredients that we have found to be essential. And while we'll discuss these in relation to Venkat's courses, both his MOOC and his blended residential course, all 5 are equally important in fully online courses, so I wanted to point that out. So here's the first. And that is that when offering an engineering course online, it's really essential to have both a technology platform and course development support that accommodate a wide range of course types. Because engineering courses include courses that are mathematical, courses that are project-based, courses that are experiential and lab-based, and so you need to have the capacity to deliver all those kinds of courses. It's equally essential to be able to accommodate different kinds of teaching methods, so lecture, but also discussion, group projects, and student presentations. So in other words, the platform and the approach need to be really flexible and also tailored to the teaching needs of engineers. And one of the particular challenges that we've found working on Venkat's course is how to best convey an equation-based course. And so Venkat's going to talk a little bit about how we approach that issue in his course, which was a very mathematical, theoretical course.
I was, at that time, when I was building the class, I was familiar with 2 perspectives for models of creating online content. As I mentioned earlier, Chris Kramer was offering a more introductory version of the Statistical Thermodynamics class, and this slide shows the approach that he adopted. What he used was PowerPoint slides with equations that would be the focus of the video, and his video lecturing would be on the side, as you can see in the top left corner. Now, the second perspective that I was familiar with was from our department head at ECE at Carnegie Mellon, Yelena Kovacevic. And in her wavelet transforms class, she used the approach that's shown here, where she would work through the equations, and that would form the focus or the main focus of the videos and the class. Now, these perspectives helped me to try and reimagine how to weave equations into videos. I think much more research needs to be done in this area, as this is the core for engineering education. Now, our philosophy was to try and reduce the cognitive load on the learner to the extent possible. So what we did was we had equations that would come in and out, and we would highlight different parts of the equation. And as I talked about a certain equation, parts of the equation would get highlighted as is shown here, where you have different parts of the equation for internal energy highlighted. And this meant that any issues that we had with any minor issues that we had with equations could be easily fixed during post-production. And the central focus of the video would be the instructor, that's me, lecturing. And I think this approach worked reasonably well given the enormous number of equations that we had in our course, perhaps 10 to 20 equations per video, video length of 10 minutes. And so I think in the end, both from an instructor's perspective and a learner's perspective, this proved to be an efficient approach. But as I said at the beginning, I think much more needs to be done on what works and in what context for engineering education. I think this is a frontier where we at Carnegie Mellon are exploring systematic ways to quantify the success of the various approaches. I think there is much learning science research that needs to be done on this frontier to try and figure out how to address the challenge of providing or generating video content for equation-dense subjects.
Great. Now, before we move to our second essential, I wanted to see if there are any questions, Aaron or Teresa, that have appeared in the chat window before we move on. How are we doing? Okay, I'm not hearing anything, so I'm going to assume from that we're good to go. But if any questions kind of rack up in the meantime, we can address them just after the next piece here. So let me move ahead and say that one of the other ingredients that we've found to be absolutely essential, really in the design of all courses, but particularly online courses, is really careful, systematic design using backward design principles. So careful design is important in all courses, but in online courses where students interact with the content first and foremost, and where there are fewer opportunities to make corrections on the fly, design becomes all the more important. And the model that we've used at ACOTAR is called the course design triangle, which is based on backward design, but basically uses these three elements: objectives, assessments, and instructions. So you begin at the end by identifying what you want students to be able to do at the end of a course or unit, and those are your objectives. Then you go to your assessments and you figure out how are you going to gauge their progress towards those objectives. And then finally, you build the instruction in order to accomplish those objectives. And so that's the course design triangle. And what we found is that a lot of attention to this early on, first of all, prevents misalignment. Misalignment comes when those three things are not working in sync, and that can create motivational problems and learning problems. Systematic design also helps to ensure that the outcomes are met. They increase efficiency by helping to prevent time-consuming mistakes and missteps. And they also promote reusability. So as Venkat will say later on, this is a time-consuming process for faculty, and if you're going to do it, you need to do it right. And so designing carefully from the ground up is especially important. And this is an idea I think that will resonate with engineers who really live by the philosophy of measuring twice, cutting once. One way at ACOTAR that we really try to foster this design approach is to offer a training course called the Course Translation Workshop for faculty, which we offer through the ACOTAR learning environment. So it's in the platform that they'll actually be teaching in. And it introduces them to these, research-based principles of online course design, while also modeling the kinds of practices that we advocate, and giving them an opportunity to interact with all of our tools before they're teaching themselves. So now I'll see what Venkat has to say about having gone through that process and what he learned about course design along the way.
the course translation workshop was I think an excellent experience for me to go through, and I think it forced me to rethink my own lecture content, and essentially there were three main things that came out of me going through the course translation workshop. The first was the way in which I taught the class in the fall of 2014. It consisted of 24 lectures. The first major change that I did was to convert those lectures into modules. Now, this turned out to be a logical step, and luckily the way I had designed the class, it was fairly modular, so it could be easily cast into this format. This goes into the reusability issue that Muni talked about. The second thing that we did was to segment the class into two halves, the theory half and then the application half. This actually proved quite nice for both the MOOC and the blended class, since this allowed people to spend time on topics that were of most interest to them. And I think this segregation also allowed people that had a more theoretical mindset to dig deeper into certain modules, and those that had a more application mindset to dig into certain other modules. And the final element of course design that really changed the way in which the content was delivered was to precisely define what each module did. In each module, at the forefront, we would precisely state what the learning objectives were, so that if people already were proficient in performing those tasks, then they could easily skip these modules. And this especially proved to be quite useful for MOOC, and for the in-class version at Carnegie Mellon, this proved immensely useful because students can then go back and see if they were able to achieve the learning objectives that were outlined at the beginning.
Terrific. So I think Aaron or Teresa is going to indicate to me if any questions do come up, and I'll just kind of forge forward and take them as they come, or address them all at the end. But so the third essential ingredient is certainly to make online courses interactive and engaging. So engaging students is extremely important online because students can easily feel disconnected, and dropout rates can be high if students feel alienated or isolated in online courses. Engagement is also incredibly important for learning, which is why there's a picture of synapses firing up here, that it's not enough just for students to do things. They really have to engage mentally with the material, or they don't learn it deeply or retain it. So engagement was a high priority for us in building this course and building our other engineering courses. But it's also a challenge in a course like thermodynamics, which is a highly theoretical course and a sort of a notoriously demanding one. So one of the ways that we decided to handle this was to, for each module, for each video in the course, was to identify some real-world application or some real-world example of the principle at work. And so Venkat and I worked very hard to kind of come up with interesting illustrations that appeared at the beginning of every video. So this first one in the upper left there was a really intriguing question that Venkat asked about why ice doesn't sink. If ice is a solid, you would expect it to sink in water, but it floats. Why is that? And that sort of created a really interesting hook that then framed all the rest of the material from that module and really made students, I think, want to learn more. So there was one on electrolytes. There was one on, well, Venkat, you can probably speak better than I can to what they were on, but we had a lot of fun filming these on campus and finding examples of the principles to illustrate the points. That was one thing we did, and Venkat is going to speak a little bit more to other ways that we tried to engage students in this course.
Yeah, yes, indeed. I think putting together those intro hooks were among the most challenging and enjoyable part of building this class. I think as Marie pointed out, thermodynamics is a very mathematical subject, and so developing intuition about this subject is very, very hard typically. And so I think these intro hooks really set the stage for what is being discussed. And I think that they have proved to be enormously useful for me to also use that as a way in which I lead all the discussion in my in-class version this fall at CMU. Now, another way in which we made sure that that there was supplemental material that would provide a more in-depth discussion, and this was provided through handouts. The handouts, an example handout is shown here, and this is an example for something known as the Ising model, which is used to describe magnetism. But as you can see, these are relatively detailed notes. And we left white space in the right margin to allow learners to write their own comments or notes. It was generally the feeling that the handouts proved to be enormously useful, and we will show some feedback at the end that supports this point. Now, another way in which we allowed students to interact, and this is a key piece for the MOOC, was discussion forums. I myself engaged quite a lot in the discussion forums. I found this to be very, very enjoyable. Oftentimes, as is shown in the example here, a question would be posed, and before I could answer, another learner in the course from another part of the world would provide an answer. Here's a discussion that Samvit Kaul is presenting on how he is surprised that a thermodynamic system maximizes a global function, that is the entropy. And he poses a question on entropy flows, which is immediately answered by Gustavo. Now, in addition to discussion forums, we supplemented this with quizzes. And the challenge with doing this fully online is that we would like this to be auto-graded. And so the auto-graded version that we used for the MOOC had multiple choice questions, numeric answers, and many other format types. However, one thing that we could not achieve is a testing of longer derivations, which I am doing in the in-class version. And this is a direction where I think there's room for further development, especially for classes that are math heavy in engineering.
Terrific. Now, if Venkat were teaching thermodynamics fully online, there are other options that he would have at his disposal to engage students. So, for example, this is from another CMU engineering course that was taught online. Students can do group work and also do group presentations via synchronous live session tools like Adobe Connect. The ACOTAR learning environment also has some functionality in it built around group work and collaboration. And one of the things we're excited about is building out this sort of suite of collaboration tools to give faculty more of a window into student groups so that they can really be a fly on the wall and see how groups are interacting and who's contributing. So this docket is one of our planned features in the ACOTAR learning environment. Now, before we move on to the next issue, I think we have a couple of questions. So, Erin, do you want to let us know what folks are asking?
Absolutely. Can you hear me now, Marie?
Yes.
Okay, great. Our first question is, lectures typically are linearly delivered. You said something about seamlessly converting lectures to modules for a course. Can you give 1 to 2 examples of how lecture content was turned into modules?
Yeah, actually, Venkat, you're the one who really modularized the content. So why don't you speak to that?
Yeah, I think I'll give an example for this. The central theme for putting a module together was to club concepts that were essentially building off the same basic principle. One example that I can give from the class that I taught was as you pointed out, I would linearly give lectures, and the lectures consisted of statistical thermodynamics associated with electrons, photons, and phonons. And as I went through the course translation workshop, I realized that there was a way in which I can unify all of these separate lectures under the theme of non-interacting systems. And when you compact those lectures into one module, so the module will now consist of 2 or 3 lectures, but they all come under the theme of non-interacting systems. Then you make a logical next step, which is interacting systems, and that's sort of how I had built the class, except that now when I made this modular format, it was even more apparent, and actually the flow of the lecture content for a learner becomes so much more easy to grasp.
Yeah, I think that's a great question about how to modularize content. It's really it's a pretty rigorous intellectual exercise to break these complex ideas down into kind of units or chunks, but it's time that's extremely well spent, both for the online course and for any residential courses that benefit from that level of organization. Aaron, you said there was a second question? Oh, sorry, Venkat, please.
Can I add? Yeah, I just want to add one more point, that I think it also helps to connect the dots between the modules. I think that is one aspect where once you convert the lectures into modules, that allows you to form the links between the modules, which is slightly more difficult when you have a linear lecture format where you say you refer to, oh, I lectured this in 2 months ago or something, as opposed to now I say this was covered in module 2.x. And I think that allows students to go back to precisely the module that would be the accompanying module for that particular lecture.
Thank you very much. We actually have 2 additional questions. The first is, I concur that faculty time in preparing materials is extensive. For me, it was 40 hours a week for 10 weeks. And the production quality is not near what I would have liked, but it seems to work. What is your experience for a 3 to 4 credit course?
Yeah, I can speak to that. I think that you're absolutely right, that it is time-consuming. It's in our experience working with different faculty, it's very variable depending on the faculty member's comfort level in front of a camera, the kind of production approach they're taking, how, whether their materials are already very modularized or in good shape, or whether they have to really work with them extensively. But in our experience, it generally takes, probably 100 to 300 hours to develop a full semester's worth of lectures, which is one reason that we kind of advocate a more sort of iterative approach, as well as some of the techniques that I'm going to be talking about in the next piece for facilitating iteration and updating, which I think was perhaps the second part of your question. Is that right, Erin?
On the adaptability?
Yes.
Yes, that is correct. Asking just how production time could be utilized since it's often done in the front end and not towards adaptability.
Yeah, so let me actually go on to the next piece because I think it speaks to that, and it's a really excellent question. So the next essential ingredient that I would identify for online engineering courses is that they be designed to allow for iteration and updating. So most engineering, well, engineering is a rapidly changing field. It's a very dynamic field. There's a need to continually update information so that it's current. And so it really does not behoove an online engineering course to have too rigid a structure that doesn't allow for that. So one of the ways that we try to build with iteration in mind is this modular structure. That's why you're seeing a very modular building in front of you. But we advocate that faculty, first of all, break content down into chunks of roughly equal size, that they make each piece as self-contained as possible so that each piece has a beginning, middle, and an end. We advise that they take out sort of references to material that came before or after in case they want to change the order or sequence or swap out a piece later. So this modular design approach makes it easier to change a piece of the course without necessarily changing the entire course. Another thing that we believe in is really matching the production style with the durability of the content. So if the content is conceptual information that is likely to stay the same, that's where we think it's worth investing in higher production values, possibly a studio or more, throwing more resources at it. Whereas for the content that's likely to change frequently, we use a lighter weight, more flexible approach. So one of the things we do at ACOTAR is we send faculty a kit, which is what you see on the right, that includes a high quality but lightweight webcam, tripod, ring light, and microphone. And this allows faculty to set up a little home or office studio where they can record video whenever it's needed. So this is maybe a good approach to adapting or continuing to work on a course after that big initial push that you identified in your question. So those are two approaches to trying to make the material more adaptable. And Venkat's going to talk a little bit too about how we tried to balance the video components versus the written components, also to allow for more iteration.
Yeah, so as Marie pointed out, I think the class style plays a huge role in what you do, how you decide to go on the video production quality. And since the class content, the way in which we had structured it and the level of the class, this would be a graduate level thermodynamics class, and most of the foundational principles are fairly solid. So, things would not change that rapidly in terms of the foundational aspects of the class. And so I think that's why, that was one of the reasons why we went for a more sophisticated video production quality in our class. Now, the way we balance the high-level conceptual information that was provided in the videos with more in-depth research content was through the handouts. What is shown here is a handout for phases of liquid water, which actually is the piece that answers the puzzle that Marie posed earlier on why ice floats on top of water. And this is even now a topic that is actively researched, and so the way in which we imagine updating content in our course is the handouts would serve as the most up-to-date resource on the information on that topic, and the video lectures are essentially meant to give the foundational aspects of the class. And so, and the handouts can be easily changed, so that gives us this flexibility that you would need for rapidly changing fields. Back to you, Marie.
Thank you. I also see another really good question from Doug here. So he asked, so what happens to the scaffolding learning paradigm? And I assume what he's referring to there is if we modularize the content and treat each piece as if it stood alone, how do we speak to what we know about learning, which is that learning builds on prior knowledge and that needs to unfold in a way that's logical and progressive? And I think that's an excellent point. I do think that both things can be accomplished simultaneously, that you can modularize content and then use the framing of that content to do what you mentioned before, Venkat, which is to build the connections between content pieces. And clearly also they need to be sequenced in a way that is logical and where the prior knowledge builds in a way that makes sense. So I actually wrote a blog on just that topic, Doug. I think it's a really good question. Okay, so the fifth piece, the fifth and final essential element, we believe, is that the technology platform has to allow for tool integration, that engineers use a wide variety of tools, many of them digital, and they need to be able to use those tools in their teaching. And these include tools like simulations, statistics packages, graphics programs, equation editors, project management tools like Piazza, code repositories. Without access to these kinds of things, it's not possible to teach some kinds of engineering courses. So So it is essential that however you offer these online engineering courses, that they be able to articulate with programs like MATLAB or Piazza or Wolfram Alpha, GitHub. And that's been a high priority in the design of the ACOTAR learning environment, is interoperability and the ability to integrate diverse tools. And to some extent, we can do that, with commercially available tools. We can have APIs and formal integrations, but we've also really tried to encourage faculty to use their own kinds of tools. So what you're seeing on screen here is from a course taught at CMU called How to Write Fast Code, where the faculty member himself had developed this little leaderboard. So this was basically a leaderboard that dynamically measured the progress of teams in relation to one another in terms of the speed of their code. So these little circles bounce and move and change where they are depending on the speed of the code that those teams have written. So we worked with this faculty member to embed this little leaderboard directly in the course that he was teaching, and we try to integrate as much as we can with the tools that faculty use. All right, so let's see, Venkat, let's finish up with a little bit of a kind of a debrief of how the Statistical Thermodynamics MOOC went, as well as your residential flipped version and what students had to say about it, and then we'll wrap up.
Thanks, Marie. So I'll sort of conclude the discussion by sharing data from student feedback and maybe talk a little bit about my plans for the future. Here's some feedback from a fellow instructor's perspective. It appears that Junko, who's an instructor in a Japanese university, he very much enjoyed the derivations that were provided in the handout and the way in which they were presented. In the next slide, Charles points to the fact that that this is one of the best classes he's taken on Coursera, and he has 20 plus under his belt. Ralph points out that he likes the format and his completing the MOOC offered earlier by Chris Kramer helped him do well in this class. Most notably, it increased his desire to continue studies on these topics. In the residential version, we've had quite positive reviews and quite positive feedback on the way in which we've blended the course content. And we've come far, but I think there is a lot more to be done. I think a couple of big challenges remain. How to incorporate step-by-step derivation while at the same time remain engaging in an online context. How do you make sure that the video is not 40 minutes long and yet you can sort of go through the derivation in a slow and sequential manner? That remains a challenge. I think another challenge associated with some of the data that we have analyzed is there is a need for more frequent quizzing. However, how do you do that without making it burdensome? I think we had videos where you would have in-video quizzes in between where this would allow the learners to pause and then think about what was the content that was provided. But I think overwhelmingly what we felt is that there's a need to connect the modules even in the way in which we test them in the in-video quizzes, and so this remains a challenge. And I think this is an exciting time for online learning, and there are lots of challenges, but there's also a lot of opportunities. Now, I would like to end by sort of offering a note from an instructor's perspective, and this also answers in part one of the questions that was raised. The benefit of building an online or blended course is only gained when the course content is of a certain quality. You sort of need to go above a certain threshold quality in order to gain the benefit of developing all this online content. Now, in order to reach that quality, it takes an enormous amount of effort. There is so much complexity in deploying a course like this. There is video recording, video editing, handouts, coordination, incorporating in-video quizzes, so many moving parts. And in my case, at least, I think ACOTAR and my collaborators took a lot of this complexity away. And this allowed me to do what I do best, which is teach thermodynamics and reimagine the course content. So with that, I will end and thank ACOTAR for giving me this opportunity to participate in this webinar. Back to you, Marie.
Well, and thank you, Venkat, and I want to point out that Venkat was also, a real pleasure to work with on this because he brought so much energy and dynamism of his own and such a commitment and dedication to this project. So it was fun on all counts. To reiterate what we discussed here today before we open it up for questions, these are 5 of the ingredients we think are essential to building an effective online engineering course. One is that the platform and the process for working with faculty have to accommodate diverse course types and teaching approaches, that it needs to be deeply rooted in strong design principles that employ backward design, that the course itself be engaging and interactive and challenging to students, that it be produced in such a way that it allows for iteration and updating, and it can accommodate dynamically changing content, and finally, that it be able to integrate the kinds of tools that engineers routinely use. So those are our 5 essentials. There's clearly more to it than that, but these I think are a really good place to start. Here's our contact information. We'd love to hear from any of you, so I'll leave that slide up as we take any questions that you have. So let's give you all just a few minutes to think and compose questions if you've got questions. And Aaron, you can give me the high sign if there's a question that you see that perhaps I don't.
Not a problem, Marie. At this time, we don't have any, but I would like to encourage anyone that has any questions for Marie and Venkat to just go ahead and ask them in the chat, and we'll make sure they're addressed now.
And if you can't stick around for Q&A and have to leave, I just want to thank you for coming and say have a wonderful day. And again, we really appreciate your participation. And we're happy to stick around as long as there are questions.
I would also like to remind everyone that the slides and recording will be made available. We'll be sending those out to anyone that attended.
I just want to thank you guys. Thank you, Shri. I got your message here in the chat. I don't have any further questions. Most of them got covered. Thanks for sharing your experience building this fantastic MOOC. Thanks so much. We'd love to hear your experiences and your perspectives on online engineering education. So please feel free to contact us and start a conversation.
All right, well, still no questions, Marie, so I think we're good to wrap up. I just want to thank you and Venkat so much for your time and for doing this wonderful webinar for us.
Thank you all. Thank you to the Learning House for organizing everything. Thank you, Venkat.
Thanks again. Thanks to ACOTAR for putting this together. I think Carnegie Mellon has benefited tremendously from this close collaboration with ACOTAR, and hope there is more work in online learning. Thank you.